So we are going to start talking about inverses in chapter 6. First thing we need, if we're going to talk about inverses, is some definitions. Not every function has an inverse. So an inverse is like the opposite of something. If I say plus 2, what would be the opposite of that? Minus 2, right? So adding and subtracting are inverse operations. If I say I'm going to multiply by 3, what would be the inverse of multiplying by 3? Dividing by 3. They're opposites. In order for us to be able to find that true opposite, we have to have what are called one-to-one functions. So if something is one-to-one, that means two different inputs in the domain correspond to two different outputs in the range. All right, we know if it's a function, that means x doesn't repeat. If it's one-to-one, what that's telling me is y doesn't repeat. If you put in two different x values, you cannot get the same y back. So first, we are just going to decide if things are one-to-one. Our functions can be represented lots of different ways. We could see, we're used to seeing equations, but we could be looking at graphs, we could be looking at tables, a list of ordered pairs, a mapping, so we need to be able to decide from any way. So this first one, I gave us a mapping. If I want to decide if this is one-to-one, so this is like our x, our input, these are the y's. If it's one-to-one, what does that mean? Look back on the previous slide. What did I write down? If it's one-to-one, y doesn't repeat. Is this one one-to-one?
No, because 38.
Okay. Two different x's give me 38 as an answer, so it is not one-to-one. Is B one-to-one? Yes, if you look at your y's, every ordered pair has a different y value. So this is one-to-one. A lot of times in my abbreviation, I just do 1-1 for one-to-one. All right. If we are looking at an equation, we have to have a different strategy. So unfortunately, if you don't have graphing calculators, you can't always just look at a graph. Okay, if it's something we know how to graph, that's one thing. If it's not, then we have to go back to the definition. The definition says if it's one-to-one, two different x's have to give you two different y values. So what we'll do is essentially the opposite of this. We will assume if two x's are the same, we'll see if we get the same y value. So if I'm trying to decide this just by the equation, okay, one-to-one means if you put in two x's, you get two different y's. So we'll start out pretending I put in two different x values. I'm going to do an a and a b. And that they are equal. So a and b here represent two different x's. If it's one-to-one, their y's cannot be equal. Okay, so now I'm going to solve this for a. So if I'm trying to get a by itself, we would subtract our 7. Divide by -3, and we get a equals b. So what I just found is the only way the y's could be the same is if I plugged in the same number to begin with. So if you solve this and get a equals b, that means it is one-to-one. The y's never repeat. The only way you can get the same y value is if you put in the same x both times. So if I look at this one, if I'm trying to decide if it's one-to-one, we are going to pretend we get the same y twice. So you just put a and b into the equation for your x and set them equal. And now we are going to solve this. So how would I get rid of a square root. Square each side. Right, then what would we do if I wanted to get a by itself? Subtract 49, I get negative a squared equals negative b squared. If I divide by negative 1, I get a squared equals b squared. How do you get rid of a square? And anytime you add a square root, what do you have to add with it? So I get a could be positive or negative. That means I can get the same x, or same y value by putting in two different x's. I could put in positive 7 and negative 7. If I put in positive 7, I get 0. If I put in negative 7, I get 0. So is this 1 to 1? No. So if you solve it and you get a equals b, it's 1 to 1. If you get anything else, then it's not. Why did this one turn out to not be 1 to 1? What part made me have to throw the plus and minus in there? Right, when we had to add the square root. So when you have something squared, it's probably not going to be 1 to 1 because you would have to add a plus and minus when you solved it. All right, we can also tell this from the graph. We know that if it's a function, x doesn't repeat, so the graph passes the vertical line test. No matter where we draw a vertical line, it only touches the graph once. If it's 1 to 1, y doesn't repeat. So what would we look for on the graph? If we hit the same y value more than once. So on the graph, we can look for a horizontal line test. If you have a graph, okay, could I draw a horizontal line that hit this graph more than once? Yes, so this one is not 1 to 1 because I have multiple points that hit the same y values. But if you have a graph that only hits something like this, okay, if I drew horizontal lines that would only hit the graph once, so that one is 1 to 1. So the graph is a lot easier to look at. You're just seeing would any horizontal line hit it more than once. So I want you guys to take a second on the next slide. These are two functions that we have graphed before, x squared and x cubed. You know what those graphs look like. What does x squared look like? A parabola. And we can see then a parabola definitely does not pass the horizontal line test. There are lots of horizontal lines you can draw that hit it more than once, which is just why on the previous one it had an x squared and it wasn't 1 to 1. Okay, what does x cubed look like? The cube root is the sideways chair. The cube is just your normal chair. And I can see no matter where I draw a horizontal line, it only hits once. So that one is 1 to 1. So, in general, if something is 1 to 1, then it has an inverse. The inverse is the opposite. So what it does is essentially reverses the x and y's. The notation is f to the negative 1. Negative 1 here is meaning an inverse, just the opposite. So if I gave you a set of ordered pairs and I asked you to find the inverse, all the inverse does is reverses the x and the y. So if negative 3, negative 27 is a point on the original graph, what would be the point on the inverse? You're not changing the signs, you're just changing the order. You flip x and y. So negative 2, negative 8 would become negative 1, negative 1 would stay the same. 0, 0 stays the same. 1, 1 stays the same. 2 8 would become 8 2. So if I give you the ordered pairs, all you have to do is put them in opposite order to get your inverse. Are we okay with that part? So you'll notice the domain of the original, the x's in the original becomes what? In this original one, my domains, my x's were -3, -2, -1, 0, 1, and 2. When you go to this one, those are the y values, so those are the range. The range of the original becomes the domain in the inverse because x and y just flip. So that is what the next slide says. The domain of the original function is the range of the inverse. And the range of the original becomes the domain of the inverse. That is very useful, especially tomorrow. We'll start really finding inverses a lot. And so knowing that property about domains and ranges would be helpful. The other thing we know is that inverses are opposites. So if I take a number, let's say my number is 7. If I add 5 and subtract 5, what do I get back? 7. Because I did both the operation and its inverse. Would it matter if I did 7 minus 5 and then plus 5? No, we still get 7. So to decide if things are inverses, we can check. If they're inverses, when you compose them, you should get back x because they should undo each other. Now it has to work for both of them. So if we're checking if things are inverses, we can check compositions and see if we get x back. So for example, if I want to decide if these are inverses, we are going to do two compositions, f composed with g and g composed with f. If we get x for both answers, they're inverses. If even one of them doesn't turn out to be x, then we can stop and say they aren't inverses. It is possible that one might work and the other doesn't, which is why we have to check both. So f composed with g means f of g of x. Do you remember doing our compositions? Start on the inside. G is 1/2 times x plus 3. I'm putting that into f. F is 2 times the thing we plug in plus 3. Compositions. You start on the inside. That was g. We plugged it in. We took that, replaced x in the other one with it. All right. If I'm working this out, 2 times 1/2 just gives me, so those cancel. So x plus 3 gives me x plus 6. I didn't get x out, so what does that mean? They're not inverses. So is there any need to even check the other one? No, I could just stop right here and say these aren't inverses. They aren't opposites, they don't cancel each other out. We'll do another one together and then I'll have you guys try one. So if I want to know if these are inverses, we're going to do the compositions. So f composed with g means f of g of x. So we're starting on the inside. G is 1/x plus 1. And I'm taking that and replacing the x in my f function. So f is 1/x is the thing I'm plugging in, minus 1. if I have to work that out, what do we do first? Okay. So we have +1 -1. Those cancel. If you want to divide by fractions, you multiply by the reciprocal, and we get x. So, do I know for sure they're inverses right now? No, but we can check the other one at this point. So now we do G composed with F. So that means G of F of X. So we start on the inside. F is 1 over x minus 1. We put that into G. G is 1 over the thing I'm plugging in. And we still have the +1 on the end. So all I did was replace the x. Alright. And if I want to divide fractions, you flip and multiply. So that gives me x minus 1 plus 1, which is x. So I got x for both of them. What does that mean? They are inverses. If one of them doesn't turn out to be x, they're not. But if they both are x, that means they undo each other. You get back what you started with. So they are inverses. I want you guys to try one. So that composed with G. You are taking G of x, -1/3 x minus 4, and I'm going to replace the x in function f with that. The function f is 3 times the thing I'm plugging in with a +4 on the end. When you do 3 times -1/3, what happens? -1 times x minus 4 plus 4. So I get -x plus 4 plus 4, or -x plus 8. Are they inverses? No. So you could stop right here and say they're not inverses. If you did the other one first, that's fine. It doesn't matter. You should get the same thing if you did G composed with F. So you start on the inside. F is 3x plus 4, so I'm going to function G, replacing my x with 3x plus 4. So 3x plus 4 and minus 4 cancel. -1/3 times 3 is -1. So again, it's not x, so they're not inverses. Any questions on deciding things are inverses? Yeah.
So on the first problem, what did you do first to get your -1? Did you times the 3 by?
Yes.
How come you wouldn't simplify inside?
You could have. So that would have given you a -1/3 x plus 4/3. And then distribute your 3, so -x plus 4. And you'll get the same point.
Okay.
So it will not matter which one you do there.
And also, on the bottom one, wouldn't that work anyway though, because if you set it equal to 0, it would be x equals 0.
But you can't set it equal to something. You just have to simplify the expression you have. It's not like solving an equation where you're getting the x by itself. Because we're not originally told this is equal to 0, so we can't throw it in. We just have to simplify what we have and see if it would turn into x. Other questions? Okay. I'm going to do one last thing, then we're stopping for today. So when we're looking at the graphs, because they are opposites of each other, and x and y just reverse, they are symmetric across the line y equals x. I think Mrs. Keller, when you guys did inverses back in Algebra 2, hopefully this stuff is kind of familiar, you did do it in Algebra 2. She used to always have you draw a dashed line at y equals x, and look if your inverse, or if your graphs were the same on both sides. You guys remember doing that at all? Maybe? So let's just take a couple. We'll try just a couple examples here, and then we'll stop with that piece for today. So if I wanted to graph the inverse of y equals 3x minus 2. Let's start, we could just graph 3x minus 2. That's a line. Y-intercept is, slope is up 3 over 1. I can't draw straight lines, so I have to put a lot of lines. So that is 3x minus 2. If you were graphing the inverse, you could take each of these points. This is the ordered pair 0, negative 2. So what would that point become on your inverse? Negative 2, 0. This is the point 1, 1. So on the inverse, it's still 1, 1. This is 2, 4. So it would go to 4, 2. This was negative 1, negative 5. So negative 5, negative 1. So here is my inverse. So we got that just by flipping the x's and y's. If you graph the line y equals x, that's a line with a y-intercept of 0, slope of 1. Do you guys see that it's a mirror image on both sides of those? If I fold it on that green line, the two overlap themselves. So that's what it means when it says the function and its inverse are reflections across the line. But easier, I think, if you have a graph, just flip your ordered pairs to get the points on your new one. All right, I think I want to stop here for today. So tomorrow, we are actually going to find the inverses from the equations. There's a Math Excel assignment open. This is the same assignment for today and tomorrow, but you can do a big chunk of it already. Let me kind of look through and I'll tell you for sure. But just as a heads up, this is due on Wednesday. Tomorrow's Wednesday, due Thursday. Tomorrow I will finish the section, but you can already do a good chunk of it. You could do 1 through 13 and 20 through 24 already.